Welcome to This Explainer. Today we're popping the hood on the statistical engine that's running inside practically every machine learning model out there. If you've ever felt totally overwhelmed by the math behind artificial intelligence, well, you are in exactly the right place. We're skipping the jargon and going straight to the core of how these models actually make their decisions, breaking it down through 10 foundational probability concepts.
Let's get right into it. The author of our source material perfectly nailed a feeling so many of us have had, writing, "I treated probability as the vegetables of machine learning, the boring stuff you choke down before you get to the good part." But here's the massive secret nobody tells you up front. A machine learning model is almost never 100% sure of anything. Whether it's picking out a cat in a photo, flagging a sketchy bank transaction at 2 a.m., or just predicting the next word you're going to type, the model doesn't actually know. It just spreads its confidence across a bunch of options and hands you the one that's most likely. Really, probability isn't just a prerequisite. It's the native language of machine learning. All right, let's kick things off with Section 1, defining the unknowns, or how models view the world before the data even arrives. Our very first concept is the random variable. Now, to ground all of this, let's think about building a spam filter for your inbox. Before an email actually shows up, you obviously don't know if it's spam or not. Any value that depends on an outcome you haven't seen yet is a random variable. In machine learning, this covers basically the whole shebang: your input features, the labels you're trying to predict, even the errors your model makes. For a spam filter, the label itself is a random variable. Before you read it, it could be spam or it could be safe. But the absolute second it gets labeled, the mystery's gone. You just have a hard number, a 1 for spam or a 0 for not spam. So we map out those random variables using concept number 2, probability distributions. Since a variable can take on different values, we have to know exactly which values and how often they happen. For simple, discrete outcomes, like a yes or no for spam, we use something called a Bernoulli distribution. And the golden bookkeeping rule here is that all the probabilities must add up to exactly 1. No more, no less. So if the probability of an email being spam is 30%, the probability of it not being spam has to be 70%. The model is essentially just trying to learn this exact distribution map. Now, once a model starts making predictions, we need a way to measure how well it's doing. That brings us to concept 3, expectation, variance, and standard deviation. Expectation is really just the average expected value. But as we know, averages can totally lie to you. Take a look at these two models predicting house prices. Both of them have an average expected error of $10,000. Sounds the same, right? Actually, no. Model A is consistently off by 10 grand every single time. Model B, though, has these wild swings, missing by just $1,000 on one house, but 50 grand on the next. Same exact average, but wildly different behavior. You would absolutely want to know this before using either model in real life. And that is exactly why we use variance and standard deviation to measure the spread of those errors, rather than just relying on the average. Moving right along to Section 2, making educated guesses and using context to update our beliefs. This brings us to our fourth concept, conditional probability. You see, a smart model doesn't just ask a broad question like, what's the probability that an email is spam? It asks something much more specific. What is the probability that an email is spam, given it contains the word free? Notice that absolutely crucial word there, given. Conditional probability is simply the chance of something happening once you already know another piece of information. The model observes specific features and asks for the probability of a label given those exact features. And it is amazing how dramatically that single condition can change the math. Let's say maybe only 20% of all your emails are spam overall. But out of all the emails that contain the word free, maybe 80% turn out to be spam. The moment the model spots that single highly useful clue, the word free, its internal probability estimate shoots straight up to 0.8 or 80%. This constant, continuous updating of estimates, that's the heartbeat of a machine learning prediction. Which naturally leads us right to concept 5, Bayes' theorem. Okay, I know Bayes' theorem has a reputation for being incredibly intimidating, but honestly, it just has a massive marketing problem. Strip away all the fancy Greek letters, and all it does is tell a model exactly how to change its mind when new evidence drops. It takes what the model initially believed, factors in how common the new evidence is, and spits out an updated belief. If spam is mostly rare, but practically every spam email screams the word free, then the second that word appears, Bayes' theorem tells the model to immediately raise its suspicion. Concept 6 takes all of this and expands it to multiple variables, because models are usually juggling a ton of things at once. A joint distribution is the probability of multiple things happening together, like an email having a weird link and being spam. A marginal distribution is when you zoom in on just one variable and totally ignore the rest. And then we have independence, when knowing about one variable tells you absolutely zilch about the other one. All this leads to a fascinating trick called naive Bayes. See, naive Bayes assumes that all the features in a dataset are conditionally independent. Now, to be blunt, that's a lie. Words in a sentence are deeply connected. They're not independent at all. But naive Bayes uses this wrong assumption to radically simplify the math, and somehow it still works wonderfully, especially for text analysis. It's basically a really, really helpful lie.
So we know how they guess, but how do they get better? Let's jump into Section 3, Learning from the Data, how models train themselves and correct their mistakes. Concept 7 is likelihood and maximum likelihood estimation, or MLE. When we train a model, we're basically asking, how well do the model's current internal settings actually explain the data we're feeding it? That measurement is the likelihood. MLE is a training strategy that says, hey, choose the parameter values that make the observed data as likely as possible. The intuition here is super straightforward. A good model should assign a high probability to the things that actually happened. If your spam filter keeps letting obvious junk mail through and saying, looks fine to me, its likelihood is terrible. MLE forces the system to keep tweaking its parameters until it correctly flags what it's seeing. Of course, to train anything, you need data. That's Concept 8, sampling, and the law of large numbers. In the real world, you literally never get to analyze the entire population. A tech giant might log 500 million clicks a day, but they only have the computing power to train a model on 3 million of them. So, can you actually trust a small slice to represent the whole pie? Well, the law of large numbers says yes, you absolutely can. It proves that as your sample size grows, the average naturally drifts toward the true expected value. This, along with the central limit theorem, is the magic ingredient. It's the sole reason we can confidently train a model on a fraction of the data and trust it to work in the real world. Now, as the model trains and spits out probabilities, not all of those probabilities carry the same weight of certainty. Enter Concept 9, entropy. Entropy measures exactly how much uncertainty exists in a probability distribution. Look at the difference here. A prediction of 0.99 versus 0.01 means the model strongly believes one answer is right. It's highly confident. In math terms, that's low entropy. But compare that to a 50-50 split. The model is completely clueless, basically flipping a coin. That is high entropy. We take that idea and use a related concept called cross-entropy loss to compare the model's predictions with the actual correct answers. Let's say the truth is an email is definitely spam, but our model predicts with 99% confidence that it's not spam. Cross-entropy is going to generate a massive penalty. It is designed to punish models severely when they are confidently wrong. Working alongside a metric called KL divergence, this penalty forces the model to stop drifting off into fantasyland and align its beliefs with reality. And that brings us to the final piece of the puzzle, Section 4, trusting the model's confidence. Because the big question is, does high confidence actually mean high accuracy? This leads to our 10th and final concept, calibration and predictive uncertainty. Calibration measures whether a model's confidence scores actually line up with reality. Think of it this way. If a perfectly calibrated model makes 100 predictions and says it's 80% confident about each one, then exactly 80 of those should be correct. The real danger is that a model can be fairly accurate overall, but horribly calibrated. It might strut around claiming it's 99% confident, but only be right 75% of the time. That kind of overconfidence is incredibly dangerous, especially in high-stakes stuff like automated healthcare, fraud detection, or even LLMs trying to decide if they actually know the answer to your prompt. That's why data scientists use metrics like the Breyer score to force a strict reality check on the model before it ever goes live. Which leaves us with this final, vital question to chew on. When an AI model proudly announces it's 95% sure about something, should you actually believe it? Well, by understanding these 10 concepts, you now know that a model's confidence isn't absolute truth. It is just an incredibly complex, highly educated mathematical guess. Probability isn't just some annoying side quest in machine learning. It is the very essence of what these systems are doing behind the curtain. Once you start viewing AI through the lens of uncertainty and probability, the whole field suddenly becomes a lot less mysterious. Thank you so much for joining me on this explainer, and keep learning.